that much. This is a lecture about machine learning with Elixir using the Axon library. And the original idea was to add machine learning to a dominoes game that I was starting to write. But that dominoes game is very complicated. UI is very complicated, and the strategy is complicated. So I decided to do something simpler, which is use machine learning for tic-tac-toe. And I'll demonstrate a little bit of the game. Hopefully it started. Let me know if my font is too small. I like small fonts. It is a little too small. So it's like tic-tac-toe, but instead of X's and O's, I use emojis. And instead of, and also the moves disappear, so it only remembers the last 3 moves of every player. So it's a little different than regular tic-tac-toe. And the other idea was that instead of just 2 players, I could have maybe 4 players, 5 players, and just make the screen bigger and see if I can have the machine learning still work with a lot more players. But with more than 2 players, it's very just random. There's no strategy here. It's kind of just randomly clicking around, trying to hope that someone else messes up. So I really just stick to the 2-player. I focus on the 2-player game. And if you have any questions, just I guess let me know in the chat. I'm not looking at the chat, so if someone can let me know if there's something in the chat for me to read. So with Elixir, there's only 2 deep learning options. There's reinforcement learning using the Stockyards RAN library, and there's deep learning with Axon, and reinforcement learning. The difference between these two, reinforcement learning is so let's say you wanted to learn any game, tic-tac-toe or chess or whatever, dominoes. Reinforcement learning would start learning from 0, from the first move to the last move. So it would start with in this case, it would start with empty grid. The first move would be, this O on the left side, then X, then O, then X, and it would learn from many games what the best moves are. And with deep learning, you can't do that. Deep learning, you're basically just, I'm treating it as a classification problem. So in the example from Sean Moriarty's book about Axon, he's using an example of training Axon to learn images of different animals. So in the training set, there's pictures of dogs and cats and different animals, and then you show it a new picture, and then it tries to predict, tries to guess what the animal is based on the training data. So I'm doing something. So I'm doing a similar problem. I say, based on the current positions on the board, what is the best move? So this is an example of a board position that I'm using. So the input would be this board position, 2 O's on the left, 2 X's on the right side. I convert this shape, this grid, to an input, which is really a one-dimensional list. It's just a list, a flat list. And then there's some hidden functions that happen in between, and it converts all of that to the output, which is the prediction of what the best move should be. So that's how I'm not really explaining the hidden part yet. If I'll get to that towards the end if someone has questions. But the idea is that the shape of this board, shape of this grid with the current positions is the input, and then it gives me a prediction of the best move as the output. So the first thing to do is to format your data in such a way that you get is basically just have good data logging. So you want to I want to log everything that represents this grid so that I can pass it in as input to the deep learning function to the deep learning model. So for this example, this is how I'm logging the moves. So I'm storing the current positions on the grid, and the oldest move, which would be the move that's about to disappear. If you saw my demo before, pieces were disappearing. So that's stored in this array, in this list, and then this is the prediction of the next move, of the best move available. So translating this grid to this input, so 000 means it's not taking, so 000. So I'm using, so I'm translating this grid to an array of from 0 to 8, so 0, 1, 2, 3, 4, 5, 6, 7, 8. Those are the positions in the grid. And then this first list will be what positions are taken on the board and by which player, player 1 or player 2, or by no one. So 000 because no one's taken that position. 112 because 112, 122, 122. And then the next list would be what are the pieces that are about to be removed from this list, if any? So 000, nothing is about to be removed. 101, 1 and 1, these two pieces are about to be removed, and 000 because none of these are about to be removed. And based on this shape of this grid, the positions on the board, position 2 is the best move for player 1, which would be right here. And all of the logging that I'm doing is from player 1's point of view. So the result will be what should player 1, the next move for player 1, what should that be? And then so I have to translate that list, that tuple, Elixir tuple, to something that the Axon library would understand. So I can't pass in a tuple, so I have to pass in a one list, and that list has to be. So I can't just pass in 0, 1, and 2 because the deep learning algorithms won't understand what 1 and 2 mean. Or if I have 5 players, doesn't understand 1, 2, 3, 4, 5. That means 5 players. So I have to translate it. So the better thing to do would be to translate those all of your inputs to zeros and ones, to binary, which it's called one-hot encoding. You translate it to zeros and ones, if you can do it. Sometimes if you have decimal places as your input, you can't do it. But in this case, I can do it. So I am translating all of these, all of the positions on the grid to zeros and ones. So this is my translation, how I translate this grid to this large list. So this is still 000. So this means that it's not taken. So 0, 1, 0, 0. So 0, 1, 0, 0, 0 not taken, not taken. The first three are not taken because on the grid they're not. No player has taken that position. 1, 0, 0, 0. It's this one. It means that piece is about to disappear. So this piece is about to disappear. 0, 0, 1, 0. Map it 0, 0, 1, 0. That's player one. That's their piece. And then this is about to disappear. So that's 1, 0, 0, 0. So it's about to disappear. Underscore means it's about to disappear for this grid in my presentation. And then the same 0, this is 0, 0, 1, 0, 0, 1, 0, player two, and so on. And then also I have to train the model on different variations of the same grid. So in the example in the book, in Sean Moriarty's book, where he's training the model to detect different types of animals, cats and dogs. You can't just give it, you have to rotate the image left and right and upside down and flip it left and right so that it learns that all of these images are the same image. It's an image of a cat, but you flip it upside down, rotate it left and right. It's still the cat. So the same idea here. This is the grid from before, and all of these around are the variations of the same grid. So I'm rotating them and mirroring them. So this grid, if I flip it left to right, I get this input. I get this variation of this grid. If I take this grid and rotate it and flip it, it's the same grid. So it's 1, 1, 2, 1 disappearing, 2 disappearing, so 1 disappearing, 2 disappearing. It's the same grid. This is mirrored upside down. This is mirrored. This is a mirror rotated to the left 90 degrees, and then this is rotated left to right and upside down. So these are all the same grid, and it should learn all these variations so that it can make a better prediction. Um, any questions so far? Anyone? Um, so for training, before I was talking about how to model the data, and now we get into the training. Um, so for training, I tried to have it play itself. So I would have two untrained models, um, and because of the way the game is going, the pieces are disappearing. Um, this game, in reality, it could never end with two very good players. Um, so for this case, I would have a lot of games that would never end. It would just go, pieces would disappear, and then just players, it would never make a winning move. So I had to limit the game to 50 moves, and then that 50 moves, it would just be considered a tie. So um, I didn't learn anything, and my program didn't learn anything either. And then the next thing I did was to create a simple opponent uh, for my model to learn from. So I created a very simple opponent with simple rules. So the first move, take the center. Uh, or if it's on the second move, basically always try and take the center. If it's the first move or the second move and the center is available, take the center. Uh, Otherwise, go for the win. So try and get 3 in a row. Go for the block. So prevent the other player from getting 3 in a row. And otherwise, just play a random move. Um, and then, so this was better. So our games ended, but there was too much data because games would last for 40, 50 moves. And a lot of those moves were not winning moves. So it was there was a lot of noise in the data. So then I decided to split the gameplay into 3 stages: opening moves, blocking moves, and winning moves. So opening moves and blocking moves are mostly the first 6 moves of the game before pieces would disappear. So I would train that myself. And then so opening moves, blocking moves, first 6 moves, and then the winning moves would be everything after that. So move number 7 up to until move number 50. And then I would ignore losses, ignore the losing moves, and ignore the ties. So I would sometimes train the untrained model against a simple opponent, and then sometimes I would use the data from the simple versus simple to get more variety in my training data. I'll show you the training data in a bit. And yeah, so now I'll demo a little bit of the code and a little bit of the game. I'll just look at the chat real quick to see if there are any questions. No questions. Can everyone see is my font size okay? I like small fonts. So is and this is code. I didn't share it at the beginning, but let me share it now. All of this code is on my GitHub. So if you want to play along, you can see the code. So I'm looking at the training data file. So this training data file has the moves that I have trained myself manually. So it's moves 1 through move 6, and there's no other moves. So the first move is, it's a little easier if I show you. So this is the training data for move 1, and I'm just printing it in a ASCII art form. So this is training move 1, so there's no one has taken any moves, no pieces are about to disappear, and it should take the center square. So that's move number 1, take the center square. And then for the second move, so the rules are in the training data. So if the opposition has taken the corner, so any corner, then play the center. So taking the corner, nothing will disappear, and take the center. And then same for here this is if the opponent has taken the side, any side, because I'm going to rotate it, then and nothing's about to disappear, then take the center. And then this is if the opponent has taken the center, then pick any of the sides. So that's the center, nothing will disappear, take the side. And I'm going to rotate it so it could be any side. And then so I'm doing this for all of the first 6 moves. So I'll just do a little move ahead into move, let's say 5. So this is the 5th move. So 4 pieces have been played, 2 by player 1, 2 by player 2. So then, in this case, player one should finish taking the winning move. So this is all take the winning move, winning move, winning move. So this is a lot of just me manually logging and training it to take the winning move or play blocking move. So in this case, this is a blocking move. So player two will win if player one doesn't play here. So player one should play to block uh, player two from winning. Uh, and this is not a winning move and not a blocking move. It is just the best move. Based on me playing, it's the best move for player one to make. Uh, Player one should take that so that on the next move, it can play here, play there for the win. So that's me training it for the first 6 moves. And then after that, just take some random data. So this is the load function in case anyone wants to see this. So it's just reading the file. There's a file with training data somewhere in here. And it's just going to read that data and load it into memory. It's in the same format as this move. This is just a list. It's just another list that I'm saving to file. And just taking a look at this is the data that's from the CPU playing itself. So this is so these single quotes means that this piece will disappear. So this piece will move for player one, and this piece will disappear for player two. So if it sees this type of shape, the best move for player one is to block player two from winning and go for the win. It's actually a win for player one. And then in this case here, I don't. So this was not a winning move or a blocking move. It's a setup move. So player one should play here because this piece will disappear for player two. And then player one can play here and go for the win up the middle. And then in this case, this is the same idea here. So player two's piece will disappear. So player one should play the corner so that it can win the diagonal. So hoping that made sense. And so that's the training data. Um, and uh, and let me just go into the model really quickly. So this is the model. This is how pretty much everyone who uses Elixir will model it. I think we're all using the same example from the library. So the input would be there's whoa, that's annoying. So for the prediction, it takes in a model, a state, and a tensor, which is just the data like this here, which is the current state of the board. So the model for deep learning, a model is not like a model in React. It's not the state of the game. A model in deep learning is a function. So in this case, the model is it's this. So it's similar to what I showed in the diagram here. So I have an input here, which is a flat list, and then I have 3 hidden layers. I only have 2 in the diagram.
Yeah, Marcus,
So
can
yes,
you zoom this code?
yeah, better.
Yes, yes.
So this is the model. So input is just the flat list here. And then I have uh, 3 hidden layers. So I have 2 in the diagram, but I'm using 3 in real life. And then the reason you would use the hidden layers are kind of for if you want to train it on nonlinear data. So I'm stealing this diagram from the MIT course. Let me make this bigger. Oh, I can't play it. Let me do it this way. So let's say you have a very simple classification problem, and you want to split this data into the red pieces and the green pieces. Without activation functions, you can only just this deep learning would only be allowed to draw a straight line between the data to try and split this data into 2 groups. But so that's why we use hidden inputs, which are introduce which use activation functions to introduce nonlinearities. So this is the same to data inputs as just if you use activation functions and hidden inputs, you can discover a better way to partition your data, so you can have a better classification. So my simple example, I'm using 3 activation functions, 3 hidden inputs. But for something like self-driving cars, you would have thousands, millions of functions, of activation functions. So the more you have, the slower the training will happen. It's just the way it is. And these are just different. ReLU 6 and softmax, those are just different types of activation functions. It's I don't really go into that because it's very complex, but in the README, towards the bottom, this is a good course into deep learning. It's but if you want to really, really learn it at a higher level, this is the MIT course. It's free. It's on YouTube. It's about 10 hours. They update it every year. But it's very, very, very detailed, and it's very, very, very good. So it goes into explanation on what onto deep learning and more and other topics like reinforcement learning and things like that. So it's a very good course. But back to the lecture. So I'm using 3 activation functions, 3 hidden inputs. So this is my model, which is just a function. Remember, your model is a function. So I take in the model. The state is so when I train the data. So when I'm using my training data to train my deep learning model, it creates a state. So that's this function. So it's training based on the training data. So it takes in the function, which is a model, and takes in the training data, and then it creates a state so that it's basically learning all of the different shapes, different positions, all of the positions from the training data, and it learns what the best move is from all of this training data. And so when I make a prediction, I pass in the model, I pass in the state from that train, from that it learned from here, and then I pass in the data, which is just the current state of the board, and it will return a prediction, and then the prediction will be, let me just show you. So it learns that the best move based on, I just took the center. So the best move for it to make would be to take the side, any side. So the prediction from this predict function is a list of weights and positions. So it's saying that this is the weight. It's a tuple, and the first thing in the tuple is a weight, and the second thing in the tuple is the position. So it's saying position 3 has the best weight. It's really all of the sides. So the first 3 moves are the sides because I trained it to learn that. If we go back to the training data, I trained it that if the center is taken, take the side. So it's saying the first, the best moves are to take the sides. So because I'm training it and I'm training it to rotate so I'm training it on different positions. So I'm training it with, so in this case, I would train it with take this side, take this side, take this side. So I'm passing in 4 different variations of this data so that it can learn what move to make. And that is the prediction. And let's see what else is there. And I think it should mirror. So it learned how to block. So it's trying to win here. I'm going to block it. It's going to try and win there. So it's really good at learning what to do. I don't know what the best move is for me. Yeah, so this is going to go on forever. Oh, no, maybe. I don't know. But in any case, yeah, so I think that's it. I don't know if there's any questions. I think that's my presentation. Let me see. Game on training data. No. Any questions?
Anyone? Some questions? Take 10 minutes to talk with the Marcos. You use the hand options to talk. The MIT course is on the YouTube, right?
Yeah, so I put the link in my README. So YouTube has the video, but you should go to the website because they have the PDF for the course. I thought they had the slides. Yes. Oh, yeah. So the slides are underneath each video, so you can download the slides for any of the videos. So this is very detailed, deep computer vision and whatever. But yeah, all of the videos are online. All the slides are on this website. So better to go to the website first and then watch the video, which goes to YouTube. It's a playlist that they update every year. New playlist. So they just updated it for 2025, but it goes back to 2018 if you want to watch. This is a lot of videos. It's probably 100 hours of videos. So 80 videos. Yeah, it's a lot.
Besides the MIT course, where do you recommend to get a better understanding of deep learning and machine learning? Have prerequisites to understand?
So if you just want deep learning, this video is pretty good. If you, it's this playlist on YouTube is pretty good. If you just want very short videos that are just to get an idea, an understanding of what neural networks are and what all of these things are, it's very good. But if you want to learn with Elixir, Then you can try Sean Moriarty's book, which is about the Axon library. Axon has pretty good. I believe Axon. I should. I do. Oh no. Oh, I'll have to fix that. Uh, Axon. They have very good notebooks on uh, on how to use the library. So if you run these, you can learn some. Um, and yeah, I mean that's basically it. I threw in this web page has this is where I read he describes how he modeled his game. So I stole um, some ideas from this GitHub project. He's using reinforcement learning. I cannot use reinforcement learning because Elixir doesn't have it. But I stole some ideas about how to shape the data, how to model the inputs so that I can get a better result, a better predictions.
Nice. I really like your presentation. I see your presentation in Denver Meetup.
Mm-hmm.
And
Yeah, the link to that meetup is in the
Okay, well,
README if anyone
do
wants to
you
watch.
do you have a plan to make the other presentations about the machine learning?
I don't know. I only did this because I had time to learn it. And I used a very simple game. And so it's a lot of I don't know if I will. If I have a good problem that I want to solve, then I will. But I don't know if I will do that.
Do you work in a company today?
No, I got laid off in December, so that's why I had time to do all of this example.
Okay. Can you share your contact if
It's
some
in it's in
company?
it's in it's in my GitHub. Idea Marcos. My Idea Marcos over LinkedIn. Same Idea Marcos. Um, same guy. Same image.
Idea Marcos.
Idea
Nice.
Marcos. So
Connect with Idea Marcos on LinkedIn. Create a big network, an ecosystem Elixir. Uh,
um,
Someone have other questions? Awesome. Okay,